Okay, let's go right ahead to the next topic. Now that we just went through the power rule along with some trivial derivative rules, let's open up the rules for exponential and logarithmic functions. The derivative of the natural exponential function stays by itself, as itself, and then the derivative of the natural logarithmic function is 1 over x, the reciprocal function. The student who like to memorize a lot of formulae may prefer these two. If we have arbitrary base, not just e but arbitrary base, then we have this formula. Exponential stay the same, but we have to multiply by log of a. And of course, when base a is e, then log of e is just 1, so we have the previous formula there. How about the next one? Similar. We have log of a this time in denominator. Effect is the same. I'm not going to use these rules very often. However, they appear a lot in our textbook and those computer exercises, computer homeworks. Let's go ahead with a couple of examples here. And the first one is a little bit confusing because there are too many x's and e's there. I've written this very problem, or its variation many times in exams, and well, I'm afraid almost every semester I get a lot of wrong answers here, even though this problem is really elementary. All you have to remember is, well, yes, all you have to remember is x is a character, x is a variable, e is a number. So e to the x power, this is an exponential function, and e to the e power, there's no x in there, that's constant. Everything else is a power function. In short, we have something like this. So e to the x power, good. X to the e power, that's power function. Ex, actually, you could have written as ex to the first power, but you don't really have to worry about first power. What is x over e? This is 1 over x times, again, first power. You don't have to worry about first power. E over x, this may look like fraction function, but no, not really. It's just power function too. E times x to the negative first power. And then the last one, e to the e power, has no x in there, so that's going to be just constant. Applying the derivative rule, exponential stay the same. E comes out, and subtracting 1 from there, we have this. And then 1 comes out, multiplied and subtracting 1, and we have 0 powers, so x just disappeared. Same here, x just disappeared. Negative 1 is multiplied, subtracting 1 from the power, we have negative 2x to the negative second power. Finally, the constant, so that's going to be 0. You can do a little bit of simplification and then end up with this notation. But as far as I'm concerned, if you stop here, I'm going to give you full credit. I'm afraid I cannot say the same about computer grading, because computer grading has, what can I say, its own mind. So you have to be a little bit careful about those. One comment here. That's because I've seen this far too many times and I'm frustrated. Why don't I just copy and paste this? Just a moment, I have to make a little bit of adjustment here and there. Okay, and then let's calculate its derivative. Okay, if you use computer algebra system, Mathematica gives you this kind of answer. Wolfram Alpha will probably give you the same thing because they're both based upon the same software, Mathematica. And then what it does is, after this inputting, Mathematica just rearrange everything into its own order that it prefers. And if you look at that order somehow, Somehow machine preferred this order, but this is not a standard order that was given over here. So if you change the order and then apply the derivative rule, then actually no, not even that. Even after change of order, where is the negative 1 over e is coming from? What is coming from where? It's all jumbled up. I mean, this 1 over e came from this one, and then this negative e to the e power became 0, went away. E to the x power became that. This e came from that. All is all jumbled up. Because addition is commutative, this expression and the original one given is the same, and that expression and the answer we just discussed are the same. However, if you write like this, it is just invitation to give me 0. I mean, what can I say? Because math is all about communication. You really have to convince the grader you understand this, and then you use all these techniques in which order in right places. But if all these orders are jumbled up, that simply means this is very strong evidence that you did not understand what you wrote. This kind of answer, just copying from this computer algebra system, will give you 0 credit. And yes, I used to give 0, and every time I give 0s, I get complaints, of course, but it's all the same. If exam had been just no calculator, paper and pencil exam, and then everybody has to put those calculators and cell phones away and then do it hard way, then that kind of answer, if that has been really the what students got, that would give the student maybe 5 out of 10 or something more than that. But in today's mathematics, when everybody assumed to have certain proficiency technology and then using it, just copying from the calculator or computer is just 0 credit. I cannot really give anything there. Sorry about the digression. Let's move on to the next topic. How to take care of these logarithmic functions. Looks like this first one is okay. Derivative of logarithmic function is going to be 1 over y. How about the others? Well, if you remember the log rules, you'll be able to simplify that. 2 comes out, 3 comes out, and what do you get? Simplifying, you get 6 log of I. So applying that derivative rule for logarithmic function, 6 times 1 over y, you're going to get 6 over y. So this was really easy problem. Is it kind of singular? No, not really. There are a lot of logarithmic functions that can be changed into much simpler problem through log rules. And bulk of those problems will be discussed at the end of chapter 3 and section 3.8 or later. However, it's a good preview to go through those kind of things at this moment. Now let's move on to some more comprehensive problems about power rules. Looks like we'll have sufficient time to finish first 2, so let's go ahead and do that. How to calculate the derivative of this function? Well, is this a good way to calculate the derivative? Take the derivative of first function, so that is 0 plus 1, isn't it? Times the derivative of second function. 2 becomes 0 minus 3 minus 4t. So this becomes 0 because it's constant. First power becomes 0 power, so we have just minus 3 coefficient. 2t squared, so 4t to the first power. Well, if you look at each individual powers, then those power forms and then the derivative computation is correct. But this multiplication That's bad. It doesn't work like that. So what is the correct way to handle this kind of derivative computation? Well, if you can't calculate the derivatives and multiply them later, you'll have to multiply before taking the derivative. Break up the parentheses, just FOIL it away. 1 times 2, 1 times negative 3t, 1 times negative 2t squared, 2 times t, and so on. Break up all the parentheses, simplify a little bit, and then we are ready to take the derivatives. 3 times negative 2, negative 6, t squared, 2 times negative 5, negative 10, t to the first power, negative 1, plus 0. So everything follows from the power rule from this point on. So what's the moral of the story? Expand and then apply the power rule one at a time. Actually, you can do the same thing for this one too. I mean, it looks rather intimidating, but if you just expand it out using, this time I use complete square formula. A plus b squared is a squared plus 2ab plus b squared. We have simplification, and then apply the power rule, one term at a time. Numbers may be a little bit big, but each individual computation is an easy computation. Just remember, expand first and then take the derivative. Okay, first two problems are done. We still have some time, so let's move on to the next type of problem here. How do we deal with fractions? Is the same kind of argument work? Can you simply take the derivative of numerator, 6x squared minus 3x plus 1 is the derivative of the numerator, and then divide it by the derivative of denominator, and then that's it. I'm afraid not. So you'll have to expand it. How do you expand it? Well, here's one standard way. Because denominator is just monomial, no addition there, you can separate the numerator. What am I talking about? I'm proposing this. Separate the numerator. And then you can simplify each term, express each term as a power function. 3 minus 2, so second power. 3 minus 1, so first power. X cancel out, nothing. And then we have negative first power this time. Now that we are done with those simplification, we can apply the derivative formula. 2x, 3 halves, negative 2x to the negative second power. This is a standard method to handle this kind of problem, and our textbooks deals with this way as well. However, some students prefer to do it this way. That is, flip up the denominator and then instead of division, make it into multiplication. So instead of dividing by 2x, multiply by 1/2 x to the negative first power. Why negative? That's because x was in denominator, flipped up. Please remember, this is not 2x to the negative second power, negative first power, excuse me. The number part, 1/2, must stay there. And then we just distribute it around. 1/2 x to the negative first power times the first term, times the second term, times the third term, times the fourth term. We have this. This has better be the same as before. And then, of course, finish the computation by the derivative formula, and then here we go. There are two ways. Separating the numerator, which is textbook method, or flipping denominator to numerator, and then expand out by multiplication. Which is easier? For polynomial over polynomial, it's a push, about the same. Now, we're going to do the same things, similar things with exponential functions later on. In that case, the second method, flipping up the denominator, solution 2 will turn out to be a little bit easier. Most of the time though, I stick with solution 1. In my experience, about half and half. About Among those students who get it right, half and half,